So a few years after Rutherford and his assistants do their experiment with the gold foil to come up with this planetary model of the atom, this model of the atom that says we got mostly empty space with a small, dense, positively charged nucleus, the electrons orbiting around that small, dense, positively charged nucleus. A guy named Niels Bohr comes along and says, you know what? There's a lot of what Rutherford says that I can buy into, but not all of it. Rutherford says this, or sorry, Bohr says this whole deal with a small, dense, positively charged nucleus, yeah, that works for me. These electrons orbiting around the nucleus, yeah, that works for me. These electrons orbiting around the nucleus wherever they want, not so much. The Bohr model of the atom is a significant advance on the Rutherford planetary model. It doesn't look like it so much if you see a picture of it, because there's a lot of it that looks the same, but some of the finer points to the Bohr model of the atom really distinguish it from the Rutherford planetary model of the atom. In fact, there's three main points, three main things that distinguish it from the Rutherford planetary model of the atom that says small, dense, positively charged nucleus, electrons orbit around in circles, essentially wherever they want. The first thing that differentiates these two models of the atoms, or that advances Rutherford's model of the atom, number one, says that electrons orbit, they orbit around in circles, but they orbit on specific levels. And those specific levels are characterized by a specific energy. So you guys have, most of you guys would have been to the Saddle Dome to watch a hockey game or a concert or something. You guys know that there's 3 levels of seating at the Saddle Dome, but there's really only one place that you can walk around the rink, right? One level, mezzanine level, where you can actually walk from one part of the arena to the other. Okay? You can be in different places, but as you're orbiting around, you need to be in a specific place. Okay? Just like electrons, they orbit around, they need to be in a specific spot. In those spots, there's more than one specific spot, but those spots that they can be in are characterized by certain energies. They always like to fill in those lower levels first too, right? You guys know that from chemistry, right? 2 electrons will fill in the first level, 8 will fill in the second level, so on. You guys don't need to remember the numbers in physics, so if you haven't taken chemistry, don't worry about that. We got specific electron levels characterized by specific energies. Well, the next thing that differentiates it is this concept that we call stationary state. What does that mean? Well, you guys think back to the beginning of our electromagnetic radiation unit. James Clerk Maxwell said that as electrons accelerate, they produce electromagnetic radiation, right? That's the source of all types, ultimately, of electromagnetic radiation. As electrons accelerate, they emit EMR. Well, if they emit EMR, then they must lose energy, right? They can't create energy from nothing. So as they give off EMR, give off energy, then they must lose energy themselves. Well, here's the problem. The Rutherford model of the atom said that electrons orbit around the nucleus in circles. When things move in circles, they experience a centripetal acceleration, an acceleration directed toward the center. They accelerate, right? They don't change speed necessarily, but they change direction. So that's an acceleration. They should emit EMR, but they don't. Okay, electrons, as they orbit around the nucleus, should emit EMR, but they don't. How do we know they don't? Because we actually do get EMR out of the nucleus, or out of the atom. So how do we know that they don't emit EMR as they simply orbit around the nucleus? Think about what would happen if this set of keys that I'm swinging around my head right now lost energy. Because that's what would have to happen, right? If electrons are emitting EMR, then they have to lose energy. What would happen to these keys as they emitted EMR as they lost energy? It would spiral into the nucleus, right? It would spiral into the middle, like the keys did. Well, then the atom, as we know it, wouldn't exist. The world, as we know it, wouldn't exist. Life wouldn't exist, because we need those electrons orbiting around the nucleus to have chemistry, right? We have no chemistry. Some of you may be happy if there was no chemistry, but we have no chemistry if we don't have electrons orbiting around the nucleus. It's as if these electrons aren't moving. They are moving. They're orbiting around the nucleus, but it's as if they're stationary. It's as if they're not moving. It's as if they're not accelerating. They're in a stationary state. That kind of makes sense? We'll say electrons orbiting should emit EMR because of centripetal acceleration. But they don't. If they did, they would spiral into the nucleus. Why? Because they're losing energy. As they lose energy, they can't maintain the same orbit around the nucleus. It is as if they are stationary. I say as if, and I underline that because they're not really stationary. It's as if they're stationary. Well, the third aspect of the Bohr model of the atom that differentiates it from the Rutherford planetary model of the atom. Talked about electron levels in the first aspect. Electrons exist on certain levels, characterized by specific energies. We talked about a little bit about those electrons want to fill in those lower levels first, 2 on the first, 8 on the second, so on. Well, electrons can make transitions from one level to the other. If they absorb energy, if they absorb the right amount of energy, that is, they can jump to a higher level. Usually that energy that they absorb is in the form of electromagnetic radiation. They absorb a photon, but it doesn't have to be. It doesn't have to be. They can get energy from another electron. Another electron strikes an electron and gives it some energy and can cause that electron to jump to a higher level. Usually it's in the form of EMR, though. If you've ever gone to the Saddledome, you know it's set in the third deck, the sport check zone or whatever it's called now. You know that it's really, really high. That's where I used to, when I moved to Alberta, and I used to go to hockey games in the mid-90s. It's where I always used to sit. It cost $8 to go to a hockey game. It was, a movie at the time was $9. A Flames game was $1 cheaper than to go to a movie. So I'd spend $8 and I'd go to a ton of hockey games. I don't like sitting in the third deck now. Too old to climb up those stairs. No. You know it's a long way up, right? Okay, if you're going to sit way up there, I've literally sat in the last row, the top row, and watched a hockey game. You know that if you go up that high, you need to have energy. You need to have had a Red Bull or something before you started climbing those stairs. To go to a higher level, you need to absorb energy to go to a higher level, right? You can't just do it without expending energy, without getting energy to get yourself up there. But you know what? Electrons, they want to fill in those lower levels first. So electrons can also fall to lower levels to fill in vacancies, right? Listen, in the mid-90s, when I used to go to hockey games and sit in the third deck for $8, Me and the people who I was with, we'd always, I mean, that was a time when 10 or 12,000 people would go to hockey games. So what would we do? We'd sit there for the first period and we'd watch seats down in the first deck, see which ones never got sat in for the entire first period. And then what do? After the first period? If we had 2 or 3 seats that had never been sat in for the entire first period, we'd move down there. And when we did, we'd kind of celebrate, kind of get a little giddy. We release energy, right? We kind of scream like little schoolgirls, right? Because we're happy that we made it down to the first level for $8. When electrons fall to a lower level, they give off energy. All right, so what does it look like? What does it look like in terms of the electromagnetic radiation or the energy absorbed or emitted when electrons are making these transitions in that third aspect of the Bohr model of the atom? Well, I want you to take a look at these 3 pictures here. And we're going to separate them by a line, separate the first one from the last 2. The first one doesn't really have anything to do with electron transitions per se. It's going to be essentially a reference for us so that we can compare the second diagram and the third diagram to something. The first diagram consists of a light bulb in this picture, but any hot solid, liquid or gas under high pressure, okay, any heated solid or heated liquid or heated gas under high pressure. If we allow that light or force that light, I should say, to pass through a diffraction grating or a prism for that matter, okay, a prism or diffraction grating will split up the white light that's coming from this light bulb, then this is what we get. We get a spectrum. We get a rainbow, right? We get like you look up in the sky, you see a rainbow with all the colors of the rainbow, red, orange, yellow, green, blue, indigo, and violet. That's what we get, okay? Nothing to do yet with electron transitions. Okay, this is what happens when we have a hot solid, liquid, or gas under high pressure. We get a spectrum produced. White light, which separated, produces a spectrum. But now, I want you to look at the second diagram here. The second diagram, this time we got a hot gas under low pressure. So there's a difference here. Hot gas still, but low pressure. It still emits EMR, but that EMR might still look like white light. But it's not truly white light. It's not all the colors of the rainbow. Combined, they might look like it, but when we separate them, we can tell it's not all the colors of the rainbow. So let's put a diffraction grating or a prism in there. Let's separate all the colors we got. What do we end up getting? Oh, look. It's not even close to a continuous spectrum. It's darkness. Darkness is where no light is emitted, with a few specific lines. A red line right here, kind of an orangish yellowish line right here, a couple green lines, a blue line, an indigo line, a violet line. Each of these lines that you see there correspond to specific transitions of electrons from high levels to low levels. Okay, electron was up here. Hey, it saw a vacancy down there in the first deck. It went down. And as it did that, it gave off electromagnetic radiation. It gave off a photon. The photon that it gave off in one of the transitions was this red one. And another transition, it was this blue one, and so on. Make sense? Not getting a continuous spectrum here, we're just getting lines of color corresponding to the transitions that took place. What do we see in the third diagram? Third diagram, almost the same as the first one, right? Let's take away this cold gas, in fact. If we take away this cold gas, it is the same as the first one. You got a hot solid, liquid, gas under high pressure. It emits electromagnetic radiation. It emits white light, all the colors of the rainbow. Pass it through a prism or diffraction grating, separates it. What do you get? A continuous spectrum. But if we introduce this cool gas, then that cool gas or cold gas will absorb certain photons, cause the electrons to jump to higher levels. When it absorbs certain photons, causing the electrons in this cold gas to jump to higher levels, what do we end up getting on the other side? Well, the continuous spectrum minus a photon right here, minus a red photon that was absorbed. A continuous spectrum minus a couple green photons that were absorbed to cause the electrons to jump to higher levels. A continuous spectrum minus a blue and an indigo and a violet photon that cause the electrons to jump to higher levels. Is that okay? What do you notice about these two spectra here? This emission spectrum that's produced when photons are produced, in this absorption spectrum that's produced when we had white light, but a few photons within that white light were absorbed or taken away. That's why we have darkness, right? Because the light was taken away, absorbed by the cold gas. What do you notice about those two spectra? Yeah, same location, same colors, right? Same photons were absorbed as were emitted there. What does that tell us about whatever this hot gas is and whatever this cold gas is? What does it tell us about the composition of them? It's the same. It's the same. Every element, every mixture of gases has its own unique spectrum. When we see a spectrum down here that matches up with a spectrum right here, we know the gas is the same gas. We just know that it's cold and absorbing energy instead of hot and releasing energy. 1 second here. So where do we use this? Like what are the purposes, the applications that we can use this in? There's all kinds of them, but one of the big ones is astronomy. We look at stars way off. Hey, look, I just discovered a star. Nobody else has ever found it before. I want to know what it's made out of. So I look at the light that it's producing. I look at it through a diffraction grating or a prism, a spectrometer. And when I do that, it separates it into a spectrum, an emission spectrum. Then I compare the emission spectrum that I see from this star that nobody else has ever observed before. I compare it with other spectra that are known and published. And then I say, oh, wait a second. There must be this gas present or that gas present in this spectrum. Real quickly here, don't need to write this down either because I'll copy it for you. We see 3 spectra here, hydrogen, helium, and sodium. Real quickly, here's our unknown gas mixture. What's present in it? What do we know is present in this unknown gas mixture based on the 3 known spectra that we have above there? Yep. We know hydrogen is in it. How do you know that? All the lines of hydrogen are present in the unknown gas. Okay, this one, this one, this one, this one, 4 of them. But wait a second. There's something else too. So we know hydrogen is present. What else? Sodium is also present because these 2 lines correspond to sodium. So we've just identified an unknown gas simply by observing the spectrum that it's produced by. That make sense? All right, that's it for today.